In this chapter, we discuss extended relational databases. Let's start with the introduction. We start by revisiting RDBMSs, which are very popular in the industry. We refresh the key building blocks of the relational model and the reasons for its success. Next, we discuss the limitations of the relational model. We then look at the various ways of extending relational databases, starting with reviewing triggers and stored procedures as two key mechanisms to make RDBMSs more active. Next, we introduce Object-Relational DBMSs, or ORDBMSs. In contrast to OODBMSs, ORDBMSs build on a relational engine, but they extend RDBMSs with OO characteristics. We conclude the chapter with Recursive Queries, which are a powerful extension to the SQL language. Remember, the two key building blocks of the relational model are tuples and relations. A tuple is a composition of values of attribute types that describe an entity. It can be created by using a tuple constructor. A relation is a mathematical set of tuples describing similar entities. It can be created by using a set constructor. The relational model requires all relations to be normalized. Consequently, data about entities can be fragmented across multiple relations, which are connected using primary foreign key relationships. Since these are based on actual observable data values, the relational model is also referred to as a value-based model, as opposed to the object-oriented model, which is an identity-based model where references are made using unobservable object identifiers. Another reason for the success of RDBMSs is the availability of SQL, which is an easy-to-learn, descriptive, and non-navigational data manipulation language. Despite the popularity of the relational model in industry, the emergence of applications dealing with complex objects such as multimedia, geospatial information systems, genomics, time series, and the Internet of Things stretched its limits and unveiled its shortcomings. Due to the normalization, the relational model has a flat structure, whereby relations can only be connected by using primary foreign key relationships. This puts a heavy burden on the performance of database applications if the complexity of the data model increases, since expansive joins are needed to defragment the data before it can be successfully used and manipulated. Furthermore, modeling concepts such as specialization, categorization, and aggregation cannot be directly supported. The relational model only supports two type constructors, the tuple constructor and the set constructor. The tuple constructor can only be used on atomic values, which implies that composite attribute types cannot be directly modeled. The set constructor can only be used on tuples, such that multi-valued attribute types cannot be supported. Both constructors are not orthogonal and cannot be used in a nested way. In other words, complex objects cannot be directly modeled, but need to be broken down into simple, manageable objects of which the data can then be spread across multiple relations. The next limitation concerns the inability to model behavior or store functions to work with the data. Finally, in their basic form, RDBMSs offer very poor support to deal with specific data, such as audio, video, or text files, which are often encountered in modern-day applications. Traditional RDBMSs are passive in the sense that they only execute transactions which are explicitly invoked by users and/or applications. Most modern-day RDBMSs are active RDBMSs since they can autonomously take initiative for action in case specific situations occur. Two key components of active RDBMSs are triggers and stored procedures. A trigger is a piece of SQL code consisting of declarative and/or procedural instructions and stored in the catalog of the RDBMS. It is automatically activated and run, also called fired, by the RDBMS whenever a specific event, such as an insert, update, or delete, occurs and a specific condition is evaluated as true. In contrast to check constraints, triggers can also reference attribute types in other tables. Assume we have two relational tables, employee and department, as you can see illustrated here. The foreign key department number in employee refers to department number in department, and the foreign key manager number refers to the social security number of the department manager in employee. The wage of an employee consists of both a fixed salary and a variable bonus. The job code attribute type refers to the type of job the employee is assigned to. The attribute type total salary in department contains the total salary of all employees working in a department and should be updated whenever a new employee is assigned to a particular department. This can be accomplished by means of the SQL trigger you see here. This is an example of an after trigger, since it first inserts the employee tuple and then executes the trigger body, which in this case adjusts the attribute type total salary in department. The trigger is executed for each row or tuple affected by the insert, and first verifies if the department number of the new employee tuple is null or not before the update is performed. A before trigger is always executed before the triggering event can take place. Assume we now also have a relational table wage, which is defined as you can see at the top of my slide. For each value of job code, this table stores the corresponding base salary and bonus. We can now define the following before trigger. Create trigger wage default, before insert on employee, referencing new as new row. For each row, set salary bonus equals select base salary, base bonus from wage where job code equals new row dot job code. This before trigger first retrieves the base salary and base bonus values for each new employee tuple and then inserts the entire tuple in the employee table. Triggers have various advantages, which you see listed here. Automatic monitoring and verification in case of specific events or situations. For example, generate a message if bonus equals 0. Modeling extra semantics and/or integrity rules without changing the user front end or application code. For example, salary should be bigger than 0. Bonus cannot be bigger than salary. Assign default values to attribute types for new tuples. For example, assign default bonus. Synchronic updates in case of data replication. Automatic auditing and logging, which may be hard to accomplish in any other application layer. And finally, automatic exporting of data, for example, to the web. However, triggers should also be approached with the necessary care and oversight, because they may give rise to hidden functionality which may be hard to follow up and manage, cascade effects leading to an infinite loop of a trigger triggering another trigger, and so on, uncertain outcomes if multiple triggers for the same database object and event are defined, deadlock situations, for example, if the event causing the trigger and the action in the trigger body pertain to different transactions attempting to access the same data, debugging complexities, since they don't reside in an application environment, and finally, maintainability and performance problems. A stored procedure is a piece of SQL code consisting of declarative and/or procedural instructions and stored in a catalog of the RDBMS. It needs to be invoked explicitly by calling it from an application or command prompt. This is the key difference with triggers, which are implicitly triggered. Consider the stored procedure remove employees at the top of my slide. This stored procedure takes two input variables, dNumber var and jobcode var, whose values can be passed on from the application. It will then remove all employee tuples from the employee table which have the specified values for both variables. Consider now the JDBC call at the bottom of my slide. We start by importing the package java.sql.callable statement, which is needed to execute stored procedures. We then create a new callable statement object using the connection object con and the method prepareCall. The two question marks represent the input parameters and can be set in the Java program. In our case, we use the setString method to set the string values of the parameters and execute the stored procedure using the execute method. This call will ensure that all employees who work in the department D112 and whose job code is job124 will be removed from the employee table. Note that a stored procedure can also return results to the Java program, which can then be processed using a JDBC result set object. Stored procedures have various advantages, as you can see listed here. Similar to OODBMSs, they store behavior in the database. The stored procedure can be compiled upfront, so no compilation is required at runtime, which contributes to the performance. They can reduce network traffic since less communication is needed between the application and DBMS. In particular, calculations on large subsets of the database can be performed close to the data in the RDBMS runtime environment rather than transferring large volumes of data over the network to be processed in the application layer. They can be implemented in an application-independent way and can be easily shared across applications and/or invoked from different programming languages. They improve data and functional independence and can be used to implement customized security rules, such as a user can have permission to execute a stored procedure without having permission to read from the underlying tables or views. They can be used as a container for several SQL instructions that logically belong together. They are easier to debug in comparison to triggers since they are explicitly called from the application. Like triggers, the main disadvantage is their maintainability. Although OODBMSs offer several advantages, such as storing complex objects and relationships in a transparent way and bypassing the impedance mismatch, few success stories have been reported in the industry. This is because they are perceived as very complex to work with, which is largely caused by the absence of a good standard DML, such as SQL for RDBMSs and the lack of a transparent three-layer database architecture. Object-Relational DBMSs, or RDBMSs, try to combine the best of both worlds. More specifically, the idea is to keep both the relation as the fundamental building block and SQL as the core DDL and DML, but extend them with the following set of OO concepts: user-defined types, UDTs, user-defined functions, UDFs, inheritance, behavior, polymorphism, collection types, and large objects or LOBs. Standard SQL only provides a limited set of data types such as char, varchar, int, float, double, date, time, boolean, etc. User-defined types define customized data types with specific properties. 5 types of UDTs can be distinguished as follows: distinct data types, which extend existing SQL data types; opaque data types, which define entirely new data types; unnamed row types, which use unnamed tuples as attribute values; named row types, which use named tuples as attribute values; and table data types, which define tables as instances of table types. We discuss these in more detail in what follows. A distinct data type is a user-defined data type which A distinct data type is a user-defined data type which specializes a standard built-in SQL data type. The distinct data type inherits all the properties of the SQL data type that was used for its definition. Consider the following 2 examples. Create a distinct type $$ as decimal 82. Create distinct type euro as decimal 82. We defined 2 distinct types, $$ and euro, as numbers with 6 digits before the decimal and 2 digits after the decimal. We can now use both when defining attribute types, as you can see in the table account at the bottom of my slide. One of the key advantages of distinct types is that they can be used to prevent erroneous calculations or comparisons. For example, if we had defined both amount in dollar and amount in euro as decimal 82, then values of both attribute types can be added and compared without any problem, which is clearly not meaningful. By using a distinct type, we can only add and/or compare between amounts either in euro or dollar. Once a distinct type has been defined, the ORDBMS will automatically create 2 casting functions. One to cast or map the values of the user-defined type to the underlying built-in type, and the other to cast or map the built-in type to the user-defined type. In other words, suppose we now wish to retrieve all account tuples where the amount in euro is bigger than 1000 and write the following SQL query: select star from account where amount in euro is bigger than 1000. This query will not successfully execute and an error will be thrown. The reason is because we have a type incompatibility between amount in euro, whose data type is euro, and 1000, whose data type is decimal. To successfully do the comparison, we should first cast 1000 to the euro data type using the ORDBMS generated euro casting function as follows: select star from account where amount in euro is bigger than euro 1000. An opaque data type is an entirely new user-defined data type, not based upon any existing SQL data type. Some examples are data types for image, audio, video, fingerprints, text, spatial data, RFID tags, QR codes, etc. Obviously, these opaque data types will also require their own user-defined functions to work with them. Here you can see two examples of opaque types image and fingerprint, which are subsequently used in the definition of the employee table. An unnamed row type includes a composite data type in a table by using the keyword row. It consists of a combination of data types such as built-in types, distinct types, opaque types, etc. Note that since no name is assigned to the row type, it cannot be reused in other tables and needs to be explicitly redefined wherever it is needed. Here you can see an example of two unnamed row types to define the name and address of an employee. A named row type is a user-defined data type which groups a coherent set of data types into a new composite data type and assigns a meaningful name to it. Once defined, the named row type can be used in table definitions, queries, or anywhere else a standard SQL data type can be used. Obviously, the usage of unnamed or named row types implies the end of the first normal form. Remember, the first normal form allowed no composite attribute types in a relation. ORDBMSs drop this requirement in favor of more modeling flexibility. Unlike unnamed row types, named row types can be used to define tables. Here you can see an example of a named row type address. This can then be used to define our employee table as illustrated below. The individual components of the named row type can then be accessed using the dot operator as in the following query. Select lname emp address from employee where emp_address.city equals Leuven. This query retrieves the last name and full address of all employees who live in the city of Leuven. Another example is as follows. Select e1.lname, e1.emp_address from employee e1, employee e2, where e1.emp_address.city equals e2.emp_address.city and e2.social security number equals 123456789. This query returns the last name and full address of all employees who live in the same city as the employee with social security number equal to 123456789. A table data type or type table defines the type of a table. This refers to a table definition, much like a class in OO. It can be used to instantiate various tables with the same structure. Consider the example of an employee type as you can see illustrated here. The employee type table data type can now be used to define two tables, employee and ex-employee, as shown here. A column of a table type definition can also refer to another table type definition using the keyword ref, as you can see here. This assumes that the ORDBMS supports row identifications. When a department table is defined using the department type, its manager attribute type will contain a reference or pointer to an employee table of a table whose type is employee type. Note that these references represent the ORDBMS counterpart of object identifiers in OODBMSs. However, unlike object identifiers, the references used in ORDBMSs can be explicitly requested and visualized to the user. As we will see later in this chapter, the reference can be replaced by the actual data it refers to by means of the deref from dereferencing function. Every RDBMS comes with a set of built-in functions, for example, min, max, average, etc. User-defined functions, UDFs, allow users to extend these by explicitly defining their own functions to enrich the functional capability of the RDBMS, similar to methods in OODBMSs. These UDFs can work on both built-in as well as user-defined data types. Every UDF will consist of a name, together with the input and output arguments and the implementation. The implementation can be written by using proprietary procedural extensions of SQL, which are provided by most RDBMS vendors, or by using external programming languages such as C, Java, Python, etc. The UDFs are stored in the ORDBMS and hidden from the applications which contribute to the property of encapsulation or information hiding. Furthermore, most ORDBMSs will overload UDFs, which implies that UDFs operating on different data types can have the same name. Two types of UDFs can be distinguished: sourced functions and external functions. A sourced function is a UDF which is based on an existing built-in function. They are often used in combination with distinct data types. Assume we define the distinct data type monetary as illustrated here. We can then use it in our employee table as shown. Let's now define a sourced UDF to calculate the average, as you can see at the top of my slide. The name of the sourced function is average monetary. The return data type is monetary, and the source function is the built-in function average decimal. We can now invoke this function by using the following query. Select department number, average salary from employee, group by department number. This query selects the department number in average salary per department as calculated using the sourced UDF we defined earlier. External functions are written in an external host language, such as Java, C, or Python. They can return either a single value or scalar, or a table of values. The relational model is a flat model, since besides a primary foreign key connection between tables, no other explicit relationships are allowed. Hence, no superclass-subclass relationships and thus no inheritance are supported. An ORDBMS extends an RDBMS by providing explicit support for inheritance, both at the level of a data type and a type table. Inheritance at data type level implies that a child data type inherits all the properties of a parent data type and can then further specialize it by adding specific characteristics. Let's revisit our earlier example to define an address data type consisting of a street address, zip code, and city. We can now specialize this by creating a subtype international address, which also adds the country, as you can see. We can now use this in our employee table definition as shown here. We can then write the SQL query at the bottom of my slide. This query asks for the names and addresses of all employees who live in a city in Belgium, starting with the 3 characters LEU. Note that the definition of the international address data type does not explicitly include the city attribute type, but the latter will be inherited from its superclass address where it is defined. We can now also apply the concept of inheritance to table types. Assume we start from the definition for employee type at the top of my slide. We can now create various subtypes for it, such as engineer type and manager type, as you can see illustrated. The inheritance relationship is specified using the keyword under. Both engineer type and manager type inherit the definition properties from employee type. As you can see, a supertype can have multiple subtypes. However, most RDBMSs will not support multiple inheritance, and a subtype can have at most one supertype. The table type hierarchy can be multiple levels deep and cannot contain any cyclic references. The type definitions can then be used to instantiate tables. Obviously, the table hierarchy should correspond to the underlying type hierarchy, as shown here. Note that the primary key is only defined for the maximal supertable and inherited by all subtables in the hierarchy. The definition of inheritance has implications for data manipulation. Suppose we have the following query. Select social security number, fname, lname, start date, title from manager. This query targets the manager table and asks for the social security name, fname, lname from the employee table, and the start date and title both from the manager table. The ORDBMS will automatically retrieve these data elements from the right table. Suppose we now have the following query. Select social security number, fname, last name from employee. This query will retrieve the social security number, fname, and lname of all employees, including the managers and engineers. In other words, tuples added to a subtable are automatically visible to queries on the supertable. If we want to exclude the subtables, we should use the keyword only, as shown in the query at the bottom. An ORDBMS will also store behavior in the database. This can be done implicitly by defining triggers, stored procedures, or UDFs, as we discussed previously. More explicitly, an ORDBMS can include the signature or interface of a method in the definitions of data types and tables. Only this interface is made visible to the outside world. The implementation remains hidden, hereby enforcing the concept of information hiding. This behavior can then be considered as virtual columns in a table. Let's consider the example illustrated here. In the employee type definition, we have now explicitly defined a function age, which has an input parameter or type employee type and returns the age represented as an integer. We can now define a table employee as shown. We can then write the SQL query at the bottom of my slide to retrieve the social security number, fname, LName, and photograph of all employees whose age equals 60. A subtype inherits both the attribute types and functions of its supertype. It can also override functions to provide more specialized implementations. This implies that the same function call can invoke different implementations, depending upon the data type that it is related to. This property is also referred to as polymorphism. Consider the example depicted here. The total salary function takes one employee tuple as input and returns the salary as an integer. We can now further specialize this function in a manager subtype as shown by the second create function statement. The monthly bonus part refers to a manager-specific add-on, which can be implemented as desired. We now have two versions for the total salary function, one for regular employees and one for managers. Suppose we now write the following query. Select total salary from employee. This query will retrieve the total salary for all employees, both managers and non-managers. The ORDBMS will ensure that, depending upon the tuple, the right implementation is used. ORDBMSs also provide type constructors to define collection types. A collection type can be instantiated as a collection of instances of standard data types or UDTs. The following collection types can be distinguished: set, which is an unordered collection with no duplicates; multiset or bag, which is an unordered collection with duplicates allowed; list, which is an ordered collection with duplicates allowed; and array, which is an ordered and indexed collection with duplicates allowed. Note that the usage of collection types again implies the end of the first normal form. Consider the type definition illustrated here. The employee type makes use of a set function to model the assumption that an employee can have multiple telephone numbers. In the traditional relational model, this had to be modeled by introducing a new relation with social security number and telephone, where both also make up the primary key, hereby assuming an employee can have multiple phone numbers and a phone number can be shared amongst multiple employees. We can now create the employee table as shown by the second SQL statement. We can then write the following query. Select social security number, fname, lname from employee where 212337500 in telephone. This query will retrieve the social security number and name of all employees who have a telephone number with digits 212337500. Note the use of the in operator to verify if the specified digits belong to the set. The definition of sets and their usage in queries can give rise to a situation in which the result consists of sets that need to be sorted afterwards. Consider the following query. Select t.telephone from D. Select telephone from employee as T, order by t.telephone. Notice the usage of the keyword T in the above query. This will transform the result of the subquery into a set of atomic values which can be sorted afterwards using the order by instruction. This will give us an ordered list of telephone numbers of all the employees. Let's now also create a department type as illustrated here. Note the use of the ref operator for both manager and personnel. The former contains a reference or pointer to a manager-employee tuple, whereas the latter contains a set of references to the employees working in the department. Instead of a set, We could have also used an array or list to store the employee tuples in a specific order. We can now instantiate this type using the create table statement. If we would run the following query to retrieve personnel data from a specific department, select personnel from department where department number equals 1, 2, 3, then we would get a set of meaningless references. We can, however, use the deref function to get access to the actual data as follows. Select deref personnel.fname, deref personnel.lname from department where department number equals 1, 2, 3. Note the use of the dot operator to navigate. In a classical RDBMS environment, this query had to be solved using a value-based join between the department and employee tables. Many multimedia database applications make use of large data objects such as audio, video, photos, text files, maps, etc. Traditional relational database systems provide no adequate support for this. ORDBMSs introduced large objects, LOBs, to deal with large objects. To improve physical storage efficiency, the LOB data will be stored in a separate table and tablespace. The base table then includes a LOB indicator which refers to this location. Also, queries will return these indicators. ORDBMSs typically support various types of LOB data such as blob, binary large object, which is a variable length binary string whose interpretation is left to an external application. CLOB, character large object, which is a variable length character string made up of single byte characters. And DB-CLOB, double byte character large object, which is a variable length character string made up of double byte characters. Recursive queries are a powerful SQL extension which allow to formulate complex queries. Consider the hierarchy amongst employees in a firm as illustrated here. Let's assume we store this in a table employee defined as employee, social security number, name, salary, manager number. Note that manager number is a null allowed foreign key referring to social security number. Here you can see the tuples in the employee table. Let's now assume we would like to write a query to find all subordinates of a given employee. This can be solved with the recursive SQL query you see here. This recursive query defines a temporal view subordinates which will be used to store the intermediate results. Such view always contains three parts. The base or anchor query that contains the seed of our recursive query is the first part. It is highlighted in red. This query will select the CEO as the starting point for the recursion, which is Jones in our case. Obviously, other employees could be selected as starting points as well. The second part is a recursive query that references the view we are defining. It is highlighted in blue. The third part is the keyword union all between the two queries to join both result sets. Upon execution, the base or anchor query returns the results at the top left. The first recursive step is then run to figure out the direct subordinates of Jones and add them to the view. This will return the result in the middle left. The recursive step is then activated repeatedly until no more rows can be added to the view. The second iteration of the recursive step uses the set of the previous step as the input value and returns the result at the bottom left. The full result of the recursive SQL query then becomes as illustrated on the right. In this chapter, we have discussed three extensions to traditional RDBMSs: active extensions, object-oriented extensions, and recursive SQL queries. The first two focused on extending the RDBMS with concepts such as triggers, stored procedures, user-defined types, user-defined functions, etc. A key benefit of this is that it allows to share and reuse code across applications. The reuse stems from the ability to extend a database with functionality which is now stored centrally rather than replicated in each application. ORDBMSs extend RDBMSs with OO facilities. They capture some of the benefits of OO while retaining the relation as the fundamental building block. Hence, they provide a softer leap for those interested in combining the best of both worlds. However, disbelievers argue that one of the key benefits of RDBMSs was their simplicity and purity, which is now lost when using an ORDBMS. On the other hand, OO purists are not happy with the OO extensions provided, since the relation is still the key concept rather than a pure OO class. In the industry, ORDBMSs have had modest success, with most companies only implementing a carefully selected set of extensions. Finally, we also discussed recursive SQL queries, which allow for more complex data retrieval. They do not improve the expressiveness of RDBMSs like the other two extensions do, but instead extend the SQL language in such a way that some inadequacies of the relational paradigm are alleviated. Recursive queries partially make up for the cumbersome way in which hierarchies are represented and navigated in relational databases. To conclude, remark that many of the extensions discussed in this chapter have been implemented in various ways by ORDBMS vendors like IBM, Oracle, Microsoft. Some implement them partially or even add more specific functionality. Hence, it is recommended to explore the options available to a particular system. The chapter is based upon our book, Principles of Database Management. In case you want more information, I'm happy to refer you to the website at the bottom.